let's remind ourselves about the Roomba.
All you do is turn it on and get on with your life. Roomba has a built-in microprocessor brain and a network of sensors developed using intelligent navigation technology. The brain and sensors allow it to move along walls, go under or around furniture, and vacuum the entire surface area of the room, all by itself. It automatically adjusts its brushes to any type of floor, linoleum, tile, hardwood, and carpets. Roomba gets under beds, couches, tables, and chairs like you never could before. Roomba is as strong as it is smart. A rechargeable power-enhanced battery generates about 3 rooms worth of maximum vacuum lifting action. There are 3 settings for small, medium, or large-sized rooms. These activate the intelligent navigation technology that guides Roomba. The programming built into the microprocessing brain then directs the unit so that it covers the surface area of the floor even though walls, furniture, and other obstructions may redirect it along the way. Roomba's network of sensors let it know when it's touched a wall and then guide it along the wall. A special side brush churns to get those hard-to-reach soils and dirt deep in the corners. Other vacuums simply do not get this close. Only iRobot could bring you such an amazing intelligent sweeper vacuum that will change the chore of vacuuming forever. Roomba!
We used this before in class. The Roomba is a home vacuum cleaner. It's basically its real-time control. Implementation, it's an example of embedded computing. This is an early version of the Roomba, but it's good enough for us. Again, we want to just use it as a quick example. We'll deal with some more complex examples as we progress. But here I wanted to point out a few sensors. Here are some central and edge bump sensors that help determine when the Roomba has run into either a piece of furniture or a wall. This is the basic design of the Roomba. There are the 2 drive wheels. So it's a differential drive robot. If you drive them both forward, the robot will go forward in a straight line. If you drive one forward and one backwards, it'll rotate in place. And then, of course, you can get any combination of curves of the differential steering. Again, it's a lot like a wheelchair. Now, a couple things about the Roomba also has, it has a suction unit which vacuums up dust and dirt, puts it into a little bin. That comes up right here through the middle. On one side of the vehicle, there's a little brush. This is for getting close to the wall, because the problem is the vacuum is sucking up here between the wheels. And so this brush is a soft, flexible brush that goes out and it'll whip up against the wall and stuff like that. It just pushes stuff out toward the middle where the big vacuum can suck it up. I'm sorry I misspoke. These are cliff sensors here. The bumper is this round thing, and it does tell the difference whether there's a bump to the side or a bump to the middle. But you also have the cliff sensors, which are really critical because you don't want the robot falling downstairs. All right. So that's just a quick overview. The modern Roombas, the more sophisticated they get, the more sensors they have. There are a bunch of other things for invisible curtains to keep the robot. Some of them have a kind of a North Star system where it can locate where it is. And there are even some sensors in the dust path, so it can measure the amount of dust getting sucked up. So if it runs into a pile of dust or something, it'll spend extra time there. So there are a number of other things that going on, and we'll talk about, or we may talk about various levels of detail. But the Roomba is a great type of product to talk about, smart product, embedded smart product to talk about. And again, we'll just talk about various aspects of it at different times. Again, the cliff sensors, these are IR. They look down and they look at reflected IR light. And so if the Roomba starts to go over an edge, it just detects, oh, wait a minute, I don't get a reflection anymore. And then it does, it takes evasive maneuvers, which are pretty straightforward. It just backs up immediately, a short distance, and then it stops and does a turn depending on whether, if only this sensor hits the wall, then it's just going to take a shallow, glancing kind of 45-degree turn to get it to try to get away from the stair, wherever it is. Now, if it's going straight to the stair, right? So then these sensors these front sensors will get excited. They'll detect the cliff, and so then you're basically heading straight to the stair. So what you want to do is take a 90-degree turn to get away from it, right? And kind of move parallel to the edge of the stair. If you hit both of these sensors, however, then you have to take a more, you're at a more aggressive angle coming in toward the stair. So instead of taking the 45-degree turn to get away, you take a 60-degree turn to get away. Okay? So, and then you just take off straight. And so that's just a quick description. What we're going to do is, here is an example of a natural language spec for our Roomba robot. Now, like I said, this is just a simplified example. It's not all the features, it's just enough to make for some complex diagrams. It'll be up to you to try to add some more complexity. And in fact, there'll be some homework problems where we will add a little bit more complexity. But the basic idea of the early generation Roomba is the central, this is a central button. And this is basically the on switch, and it just says clean. Okay, we tried to make it as simple as possible. In fact, Rod Brooks used to tell the story that the very first Roomba, first generation of the Roomba, you had actually 3 buttons. It had a small, medium, and large room buttons. So you would actually select which one you thought you were in. And it confused people. And so they just said, look, just give one button clean. And of course, more recent generations, they self-dock, so they self-recharge, and they can just deploy on their own, for example, and they can know the difference between night and day and all kinds of things like that. But again, we're just going to look at a simplified version with just a few features. Okay, so here's a natural language spec for the Roomba. It's assumed the Roomba is placed in the center of the room, and then the clean button is pressed. The robot starts the suction motor and then loads the spiral trajectory and starts moving in a growing spiral to cover the room. If a bump sensor is activated, the robot rotates in place away from the sensor direction, and that would be either right or left, up to 90 degrees. Try to align basically with the wall sensor peak value. So it can then make a movement along the wall. The robot then moves forward in a straight line after finding that peak. Now, at any time, if the cliff sensor is activated, the robot will back up 1 centimeter, then rotate 90, 45, or 60 degrees based on the cliff sensor activated, which is either the forward, the edge, or both, right, respectively, for those 90-degree, 45, and 60-degree rotations. And then, again, it's going to transition to moving into a straight line. So the idea is from above, right, the Roomba is going to start, when you first press the button, to go in this spiral trajectory and go out and out and out. And eventually it's going to run into something. And depending on where the bump, it's going to switch into a straight trajectory, but it's going to rotate and head off in that direction based on where it hit. But it's going to search also to see if it's a wall. Now, something as small as a table leg like this, or a couch leg, it's probably not going to see that at all. It's going to decide, okay, I'm not at a wall. But if it actually gets a consistent peak of reflection, then it assumes it's a wall, and it'll kind of just take off in the direction roughly parallel to the wall. Okay? So simple robot, much simpler than the actual advanced generation Roombas that you can buy in the store today or online, but enough to get us going. Okay? So, like I said, this kind of specification, this kind of description is really important. And it's going to be required in this class. Now, we're going to talk about flowcharts.